So topic 13 is going to cover discrete probabilities, and we're going to break this into a sequence of 3 videos. So this first video is just going to be a basic introduction to discrete probability. So we have some jargon that goes with discrete probability. We have an experiment, and an experiment is simply a procedure that yields one of a possible set of outcomes. So for example, your experiment could be flipping a coin, and flipping a coin generates possible outcomes, tails or heads. So an experiment is anything you do: flip a coin, roll dice, draw balls out of a bucket. Anything that you do that generates outcomes is an experiment. A sample space is just the set of all possible outcomes that happen when you conduct your experiment. So the sample space for flipping a coin would just be a set, call it a sample space, set notation. It's just a set that contains the possible outcomes. So in the case of flipping a coin, you can get a tail, you can get a head, and that constitutes the sample space. It's everything that can possibly happen if you conduct the experiment. An event is simply one thing that can happen when you conduct the experiment. So for example, you could have event, if you flip a coin, you could have event 1 be the event that you obtain a tail. Event 2 could be the event that you obtain a head. These are subsets of the sample space. And mutually exclusive events are simply events that are members of disjoint sets. So for example, the event of getting a tail is disjoint from getting a head. Those two events can't happen simultaneously. You can't get both a head and a tail, so they're mutually exclusive events. They come from disjoint sets. So another example would be rolling a standard 6-sided die. So if we assume that the die is fair in the sense that all 6 of the outcomes are equally likely, the outcomes in the experiment of rolling a 6-sided dice are just going to be the numbers 1, 2, 3, 4, 5, 6. And the sample space, S, is just going to be the set that contains the numbers 1, 2, 3, 4, 5, 6. And we could talk about different events that could happen when you roll a die. So for example, you could have the event that you get an even number. So the event E, that you get an even number. The event O, that you roll an odd number. The event B, you roll a number greater than 3. These are all events, and we could represent them using sets. So the event set, the event or the set that contains the even numbers that you can get from rolling a die is the set 2, 4, 6. The set of odd possible numbers are 1, 3, and 5. And the set B, which was rolling a number greater than 3, B is just the set that contains all the numbers on the die that are greater than a 3. And then we could ask questions like, are the events E and O mutually exclusive? And the answer is yes, because you can't be both even and odd. And integer cannot be even and odd. Are E and B mutually exclusive? So the set E, that you're an even number, and the set B, you're a number greater than 3, we see that they're not mutually exclusive because even numbers include the numbers 4 and 6, and the set B, which contains numbers greater than 3, has 4 and 6 in it as well. So there are some differences between the two sets, but there are overlap in the two sets. In other words, the intersections are not empty. They're not mutually exclusive because the intersection even intersect with numbers greater than 3 isn't an empty set. It contains the numbers 4 and 6. So we could look at down here the even and odd. If we took the even set and the odd set and looked at their intersection, we would see that the intersection is empty, which is why they are mutually exclusive sets. Another possible experiment is to flip a coin twice and record the sequence of heads and tails. So what is the sample space for the experiment? Well, the sample space would contain all possible outcomes when you flipped a coin twice and recorded the results. So we could get a tail followed by a tail on the second flip. We could have a tail followed by a head on the second flip. We could get a head on the first flip and a tail on the second. And we could get a head on the first flip and a head on the second flip. So there would be the sample space. And then E, the event that we get at least one tail, would be everything that contained a tail in it. So E would be the set that contained at least one. So two tails contains at least one. A tail and a head contains at least one. A head followed by a tail contains at least one. And we see that head is excluded from that set. Describe in words the complement of E. So remember, the complement of E is everything in your universe of discourse that isn't a member of E. So in this case, the sample space is the universe of discourse in terms of set theory. The sample space is the universe of discourse. And remember from set theory that to get the complement, the E complement, is just going to equal the elements in the sample space minus the elements in the set E. So this is going to be everything in the universe of discourse minus those elements that are in E. So if we take everything in S and we take away the elements that are contained in E, that leaves us with E complement, which is just the set that contains the roll head. So now we need to talk about the probability of an event. So the probability of an event E, which is a subset of a finite sample space S of equally likely outcomes, is given by, so this is the probability of E equals, and we have these absolute value signs on the sets. So remember from set theory that this is the cardinality of E. This is the cardinality of S. Or in other words, this is the size of E. The size of E. Or in other words, the number of elements in E. And that's why we took some time doing counting theory, so that we can count the number of elements in a set of objects so that we can then do probability, or finite probability. Discrete finite probabilities is what we're going to be focused on. So the size of E is the number of elements in E divided by the number of elements in the sample space. So this is how probability is defined. You need to be able to count the number of elements in the event you're interested in. You need to be able to count the number of elements in the sample space. And this ratio, number of elements E, because the size of E, which is just some subset of S, the size of E can be anywhere between 0. It can have nothing in it. It can't have less than no elements in it. And it has to be less than or equal to the sample space itself. So E is going to run between 0 and the size of the sample space, which means that the ratio size of E over size of the sample space is going to run between 0 and 1. So what do we mean by a finite sample space? Well, we could talk about, how many numbers are there between 1 and 10? How many numbers between 1 and 10? Well, on the number line, if we plot the numbers 1 and 10, there's infinitely many real numbers between the number 1 and 10. So we could talk about the sample space that contains all of the numbers 1 through 10, excluding 1 and 10. So we could say how many numbers, for example, are on the open interval from 1 to 10. Infinitely many of them. There's all the rational numbers, all the irrational numbers. There's infinitely many numbers on that interval. So that sample space, it's a legit sample space, but it would not be a finite sample space because it contains infinitely many items. If, however, we asked how many integers there were, be on the open interval from 1 to 10, how many integers are there? Well, there would be 2, 3, 4, 5, 6, 7, 8, 9. There would be 1, 2, 3, 4, 5, 6, 7, 8. There would be 8 elements in the sample space of integers on the open interval from 1 to 10. That would be an example of a finite sample space. You can count how many elements there are, and you will wind up with a natural number or counting number as your answer. When we talk about outcomes being equally likely, what we're talking about is the idea that the probability of the outcomes or events need to be the same. So for example, if we have that 6-sided die that we talked about a moment ago, the numbers 1 through 6 are equally likely if on any roll of the dice you have the exact same probability of getting any one of those numbers. If the dice has been weighted so that one number occurs more frequently than others when you roll, then you would have you would have outcomes that were not equally likely. So for the first part of this topic, we're going to be looking at events that have equally likely outcomes. We'll shift gears towards the end in another video, and we'll talk about events that are not equally likely and how to deal with those. So an example. A bucket contains 4 red balloons, water balloons. It contains 5 green water balloons. What is the probability that a green water balloon is chosen randomly for the bucket? So first you need to identify what's the sample space that we're talking about. And the sample space is just all of the water balloons. All the water balloons in the bucket consist of the sample space, which means that the size of the sample space is going to equal the red balloons plus the green balloons. So I could say, hey, I have a set that contains red balloons, plus I have a set that contains green balloons, and you can't be a red and green balloon at the same time. So the size of the sample space is just going to be the sum of the sizes of these subsets. So the size of the set that contains the red balloons is 4 because there are 4 red water balloons. The size of G is going to be 5 for 5 green water balloons, and we get the size of the sample space is 9. And we want to know what is the probability that we get a green water balloon. And we recognize that the size of the set that contains the green water balloons is size 5. So the probability that we get a green water balloon is just going to be the number of green water balloons divided by the number of water balloons in the sample space. So 5/9 is the probability. And it's not uncommon to convert these into decimal numbers or decimal approximations. Again, if you convert it to a decimal, you should get a decimal number between 0 and 1. And the answer keys, I'm going to tend to leave answers in their fraction form. I want you to have the understanding that it's going to be really common in textbooks to convert those to decimals or decimal approximations. Another example, two dice are rolled and the numbers are summed. What is the probability that the sum of the numbers is 7? So the sample space in this case is going to be all possible sums that can happen when you add the result of rolling 2 dice. And we're going to assume that those dice are 6-sided. So let's assume 6-sided. It doesn't specify, so we're going to make an assumption. So assume 6-sided die, and we're going to assume that they're numbered 1 through 6. So a traditional die, not something that you would be using, for example, in a role-playing game. So this is kind of a classic example to have in a discrete probability course, and it's a good example to have because it looks at how to organize the information. So an easy way to organize the information is to look at rolling the two dice. One of the dice contains the numbers 1, 2, 3, 4, 5, 6. The other dice contains the numbers 1, 2, 3, 4, 5, 6. And then what we can do is take their sums. So we'll take their sums in a table form. I have a very unsteady hand today. I was doing an online lecture earlier and having a heck of a time controlling the pen on the pen pad. And that continues this afternoon. And I will just have to live with it. So I'm going to organize these in a grid form. Again, having a consistent way to organize things is wise. So the way that we'll do this is we roll one dice, then roll another. So this is, maybe this is dice 1, and this row here represents your roll on dice number 2. And we just take the sums. 1 and 1 is 2, 1 and 2 is 3, 1 and 3 is 4, 1 and 4 is 5, we'll get a 6, 6 and 1 is 7, and we'll just go through and systematically add everything up. 3 and 1, 3 and 2, and we should have Jeopardy music going on in the background while I fill this out. That way you have some entertainment value going on in your life. 5 and 1, 5 and 2, and you can see these just increment by 1. So once you figure that out, it becomes kind of mind-numbing. So this is everything that can possibly happen. So the sample space is going to be the listing of all of these sums, and they're distinct sums. So you would actually list, there's 6 times 6, 6 rows by 6 columns. There's 36 elements. So the sample space is the set that contains each of these sums, and the size of that sample space is 36. There's 36 possible distinct sums that you can get by adding the sum of two dice. And this says, what is the probability that the sum of the numbers is 7? So you just need to look at this diagonal right here, contains all of the ways you can make a 7. So the event E, we'll call it sum is 7. The size of E will be the number of 7s we can get. So there's 1, 2, 3, 4, 5, 6 ways to make a 7. And so then when we talk about the probability, it's going to be the probability of a 7. The probability of the event that the sum is a 7 is just going to equal the number of ways to get a 7 divided by the number of possible sums when you sum the roll of two dice. Two dice. So die is singular, and dice is plural, so it has a non-standard pluralization. So size of E is 6, the size of the sample space is 36, and that simplifies to 1/6. You have a 1 in 6 chance of getting the sum to be 7. Lottery tickets. So here's another example. So you buy a lottery ticket in the state of Washington. That lottery ticket that you pay $1 for gives you 2 plays because you get 2 rows of 6 numbers. You get 2 rows of 6 for your $1. And the way that it works is they randomly select numbers between 1 and 49, 1 and 49 inclusive. So 1 and 49 are possibilities. And you can either pick them yourself or you let the computer pick them for you if you're lazy like me. So if you buy a lotto ticket, the question is, what is the probability that you win? So we need to think about what the sample space is in this case. So the sample space is going to be all possible 6-number sequences that contain numbers 1 through 49. And I'm going to be selecting without replacement, because if you select the number 49, it isn't there to choose again. When you take it, it's removed from your ability to select it in the future. So we could think about this a couple different ways. We could say, hey, the size of S, what's the size of S going to be? Well, we could think about what happens when we pick 6 numbers. You have 1, 2, 3, 4, 5, 6. Well, the first time you pick, you have 49 choices. And then the rule of product would say your second step is select the next number. But we know that we're picking without replacement. So your next choice, you'd have 48 choices. And when you picked again, you would have 47 choices times 46 times 45 times 44. So we could directly get at it using the rule of product and our counting principles. We could also look at this as combinations, right? So we just did combinations and permutations. So we could say, hey, we have numbers 1 through 49, so there's 49 numbers to choose from. So we could say, hey, the size of my sample space is actually going to be, there's 49 numbers and I need to choose 5. And I would use combinations, not permutations, because the order doesn't matter. It doesn't matter if you get the 49 on the first draw of the ball or the last draw of the ball. A 49 is a 49 on a lottery ticket. You don't have to match the order of the numbers that are drawn. You just have to have the numbers that are drawn on your ticket. So the size of the sample space, we could actually calculate that by using combinations. And then we could say, hey, what's our event? Our event is that we have a single, our event is we have one lotto ticket because we only spent $1, which means the size of our event is just 2 because the lotto ticket has two 6-digit number sequences on it. When you buy that lotto ticket, they give you 2 chances to win. You get 2 plays. So the probability that we win, which means it's the event that a number sequence on our lotto ticket gets picked, is just going to be the 2 over the 49 choose 5. And if you calculate 49 choose 5, you get 13,983,000. I calculated this ahead of time, 816. So I'm glancing down on the paper to read that number off. And that didn't show up very nicely, so we'll fix that. That was a 13. And this simplifies to 1 over 6,991,908. So if you buy a lotto ticket, you have about a 1 in 7 million chance, about 1 in 7 million chance of your number being drawn. So you can see it's a good investment. A good way to try to invest in your retirement is to buy a lotto ticket, and you have a 1 in 7 million chance of retiring with them only hitting you for probably, what's the tax rate you think on that? 50%, 60%? Probably hammer you pretty hard. Find the probability that a hand of 5 cards in a game of poker contains 4 cards of the same kind. So just in case you aren't familiar with a deck of cards, the deck of cards contains an ace. It contains the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a deck of standard cards in the US. Why don't you look up in Google a Russian deck of cards? They're different. I have one set in my office. They aren't the same. But in the US, this would be a standard deck of cards, and then we would have a jack, a queen, and a king. So important things to note, there are 13 types of cards, so 13 card types. And in the standard deck of cards, there are 4 of each type. 4 of each type of card. And 4 times 13 is 52, so there's 52 cards total in a standard plain deck. And so we want the probability that a hand of 5 cards in a game of poker contains 4 cards of one kind. So it doesn't matter the order that the cards are in your hand. So this is going to be a combinations game, not a permutations game. And we can look at how many cards are there, how many hands of 5 cards are possible. So the sample space S is going to be all possible. 5 card hands. And we're going to get that using combinations. We're going to say the size of S, the size of the sample space, is just going to be there are 52 cards. And to get a 5 card hand, you need to choose 5 of those cards. The order doesn't matter, so it's combinations, not permutations. So here's the size of the sample space. And we have an event that we're interested in finding the probability for. And the event is 4 of a kind in your hand. So in your hand, for one of these 13 types of cards, you need to have all 4 of them sitting in your hand. So we're going to use rule of product here. We're going to say it's going to be a 2-stage process. First, we're going to select one of these 13 types of cards that are going to be that will be the type of card for which we have 4 of them. So I'm going to start off for the size of E. I'm going to say, hey, the size of E is going to be, start off by, there's 13 types of cards, and I want 4 of one type or kind. So 13, I'm going to choose one of those 13 types to be my 4 of a kind. And once I do that, the next step is, there's 4 cards of that type. I need to pick all 4 of them. There's really only one way to do this. I could get away with leaving this step out, but I shouldn't. So 13, choose 1. Then from that 1 that I choose, I have to select all 4 cards. Now from the cards that are left, I've pulled 4 cards away from the 52, which means there's going to be 48 cards left in the deck. To get a 5 card hand, I will need to choose one of these. So this is going to be the size of the event that I have 4 of a kind in my hand. And so I can look then at the probability of that event, which is just going to be the number of elements in E. And I need to divide by the number of elements in the sample space, which is 52, choose 5. And to work this out ahead of time, I crunched all these choosies out. And I got to 624 in the numerator, and I got 2,598,906 different possible card hands. And then this actually simplifies to, you have a 1 in 4,165 chance of pulling a 4 of a kind in a single deal of the cards. And again, just as a reminder, it's very common to convert these to decimal approximations. I'm not going to do that in this video, and I'm not going to, in the homework, I won't give decimal approximations in the answer key. I'll be okay if you report reasonable decimal approximations though. So what is the probability that a poker hand contains a full house? So a full house in poker is simply you choose one of the card types, let's say a king, and 3 of the 5 cards have to be the same type, and then the remaining 2 cards have to be the same type as well. So you could have a 2 and a 2. So 3 kings and 2 2s would be a full house. 3 4s and 2 5s would make a full house. And there's a couple ways we could get at this, and we would wind up generating the same result. So the event that I have a full house, I don't need to worry about the sample space because it's still going to be 52, choose 5. These are still 5 card poker hands. The event that I get a full house, the size of that event, there's a couple ways that we could calculate this pretty easily. So one way is straight combinations. I could say, hey, there are 13 types of cards. I'm going to start in stage 1. I'm going to pick one of the 13 types to have my set of 3. So once I choose the card type that I'm going to have in my hand, I need 3 of them. There are 4 of each type of card. I'm going to choose 3. Step 2 would be I already chose one of the types to be my 3. Now that I need to choose from the remaining types to choose my 2 cards, so it's going to be 12 left. I could say from the 12 types of cards that are left, I need to choose one type to have my 2 cards. And there will be 4 cards of that type, and I need to choose 2 of them. I'll have 3 plus 2 is 5 cards in my hand. I could also calculate this using permutations. And the idea would be, if I'm going to choose 2 cards, and then I will choose 3, I would choose 3 of the first card I select and 2 of the second type of card I select, then order would matter. So in other words, if I chose king then ace, I would have 3 kings and 2 aces. If I chose ace then king, I would have 3 aces and 2 kings. So what I could do is use permutations. I could say, calculate the number of permutations of 13 cards chosen. I need to choose 2 permutations, or 2 R combinations coming from a set of 13. And then once I do that, for the first one, I will do 4 choose 3. And for the second one that was chosen, I will do 4 choose 2. Calculate this either way, you're going to find that this calculates out to 3,744. So the probability that I get a full house is going to be either one of these 2 guys in the numerator, 3744, over the total number of cards, which we calculated up here as 2,598,906, and that simplifies to 6 in 4,165 chances. So I have a better chance of getting a full house than I do 4 of a kind. So here's a theorem. Let E be an event in a sample space S. We want to find the probability of E complement, the complement of E. What's the probability of everything that isn't E? And the claim is that the probability of the complement is just going to be 1, which represents 100%, or everything that can happen in the sample space, minus the probability of E. So the proof of this would be to identify that, to calculate the I'm not going to write this nicely like a formal proof. Just want to get at the justification for it. So the probability of E complement, well, we know from the definition of probability that it has to be the size of E complement divided by the size of the sample space. But how do we calculate the size of E complement? Well, remember from set theory that if we have a universe of discourse, then the size of E complement is just going to be the size of the universe of discourse, the size of everything, in this case, in our sample space, because our sample space is our universe of discourse, minus the number of elements in E. So this was from set theory. So we could replace the size of E complement with the size of S over the size of E, and this would be all over the size of the sample space. And this is going to equal, I can break this into 2 fractions because I have a common denominator sitting here. I get the size of S over the size of S minus the size of E over the size of S. And this is going to be 1. The size of S divided by the size of S is just 1. And by the definition of a probability, the size of the set E divided by the size of the sample space is the probability of E. So there's the justification for the formula. And the reason this formula is useful is sometimes when we want the probability of an event, like the probability of E, sometimes the probability of E complement is easier to calculate, And we can use the probability now of E complement to get at the probability of E just through simple manipulation, right? The probability of E complement is 1 minus the probability of E, then we know that the probability of E is also going to be, by simple algebraic manipulation, 1 minus the probability of E complement. So an example of using that: a sequence of 10 bits is randomly generated. So 10 bits, a sequence of 10 zeros and ones. And it says, what is the probability that at least one of the bits is a 1? So the issue is, and did I give myself too slow? No, I didn't. So the issue is, if I wanted to calculate the probability of at least one bit, at least one of the bits being a 1, I would have to look at, well, what's the probability that there's only one 1, plus, what is the probability that there are exactly 2 1s, plus what is the probability that there's exactly 3 1s in the sequence of 10, plus blah blah blah, plus what's the probability that all 10 are 1s. And so I have this sequence of probabilities that I would need to calculate and then add up. Well, the idea is that E complement is going to be easier to calculate. What is the probability that there are no 1s? Well, if I have a sequence of 10, and if there are no 1s in it, it means there are all zeros. There's only one way for this to happen, right? This is really 10 slots to put a 0 or a 1. Choose 0 of them to put a 1. That's how you generate a sequence of all zeros. And 10, choose 0. There's only one way to do that. When you run this through the combinations formula, there's only one way that you can choose none of something, and that's simply to not choose any. So E complement, which is no 1s or all zeros, the size of E complement is trivial. It is just given by 10 choose 0 1s, which is just 1. So the nice thing here is I know that the probability of E complement is just equal to 1 minus the probability of E, and I'm interested in the probability of E, where E is the event that I have at least one number 1 sitting there. Okay? The next thing I need to do is figure out the size of the sample space. So the sample space is going to be all possible ten-bit sequences. And when you look at a 10-bit sequence, well, how many possibilities are there? Well, for each slot that you have, there are 2 possibilities. I either get a 0 or a 1. 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 So you're going to wind up with the product of 10 2s. 2 times 2 times 2 times 2, because there's 2 choices at each stage. I either pick a 0 or a 1. So there's going to be 2 to the 10th possible sequences of 10 bits. So the size of S is just going to be equal to 2 to the 10th power. So if I want the probability of E complement, if I want the probability of E, I know that the probability of E, I can calculate the probability of E is just going to be 1 over 2 to the 10th power. Hopefully I calculated that ahead of time. It's going to equal 1 minus the probability that I'm interested in. So by algebraic manipulation, we get that the probability that I have at least 1 is going to be 1 minus 1 over 2 to the 10th power, which is going to be equal to 1 minus 1 over, and 2 to the 10th comes out to be 1024. And if you simplify this, you wind up getting, you get a common denominator. This 1 is 1024 over 1024. So you wind up getting 1023 over 1024. So the other thing that we're asked to calculate up here, it says what is the probability that you have at least 3 of the bits being a 1. So if we let the event I'll call it E2, that we have at least 3 1s in our sequence, what we're going to do is go 1 minus the probability that there are no 1s minus the probability that there are 1 1s minus the probability that there are only 2 1s. So the probability that there are at least 3 is going to be 1 minus the complement, which is going to, the complements are going to be 1 minus the probability that I have no 1s at all, minus the probability that I have exactly 1 1 in my 10-bit sequence, minus the probability that I have exactly 2 1s in my 10-bit sequence. So it's going to be 1 minus, well, what's the probability that in a 10-bit sequence I have no 1s? Well, that would be 10 slots, choose none of them for a 1, minus what's the probability that there's only 1 1 in the 10-bit sequence? Well, that's going to be 1 minus, well, and each of these have to be, the probability have to be over the sample space. So this is really over 2 to the 10th. And then I have 10 choose 1 slots for a 1 over the size of the sample space, and then I get 10 choose 2 slots to put a 1 over 2 to the 10th. So the probability that I have at least 3 would be 1 minus the probability that I have no 1s minus the probability that I have exactly 1 1 minus the probability that I have exactly 2 1s. And calculate this out. I'm getting over into a bad spot over here because that's where my head is showing up probably. So I'm going to erase this here for a second. I need to give myself some writing space. I'm out of space. So the probability that I have at least 3 1s is going to be 1 minus 10 choose 0 winds up being a 1. So I get 1 over the 2 to the 10th is the 1024 minus 10 choose 1. There are 10 ways to do that. So over the 1024 minus, and when you calculate 10 choose 2, you get 45 is what you get. You get 45 over the 1024 equals, here's a 1, get your common denominator right. This is really 1024 over 1024. So we get a bunch of stuff over 1024. We get 1024 minus 1 minus 10 minus the 45. And when we work that all out, we get 968 over 1024, which simplifies to 121 over 128. So we have another theorem. So what if we have 2 events, and we want 2 events in a sample space S, and we want the probability of the union, the probability of either E or E2, E sub 1 or E sub 2 happening. And the claim is that the probability of the union is given by the probability of E1 plus the probability of E sub 2 minus the probability of the intersection of the events E1 and E2. And this should look like the principle of inclusion exclusion because it is. But if we're going to prove this, we would just say, hey, I want to calculate the probability of the union of 2 events. Okay. But you know from the definition of a probability that's going to be the number of elements in the union divided by the number of elements in the sample space. Well, from set theory, how do you calculate the number of elements in a union? Well, you use the principle of inclusion-exclusion. You say, hey, if I have the union of two sets, I can add the number of elements in set E1 plus the number of elements in set E sub 2, but there might be elements in the intersection and I just double counted them, so I need to subtract the number of elements in the intersection one time to get rid of the double count. And this is all still over the size of the sample space. Well, if we keep working this through, we see we have a common denominator, so we can break it up into three distinct fractions using the common denominator, the size of S. Here's the size of the intersection divided by the size of S. And when you look at these, what do you get? You get the size of E1 over S, but that's just the probability of E1. And the number of elements in the set E sub 2 over the size of the sample space is just the probability of E sub 2. And the number of elements in the intersection divided by the size of the sample space is just the probability that the intersection occurs. So it really is the principle of inclusion-exclusion driving this right here. And of course, if the intersection is empty, right, if E1 and E2 are mutually exclusive, that means that E1 intersect E2 is equal to the empty set, which means that the size of E1 intersect E2, because there's nothing in there, the size of it is 0. So if this is a 0, then hey, if they're mutually exclusive, we just sum the probabilities. So an important thing usually is to determine whether you have mutually exclusive events or not. Do I have to worry about subtracting off the probability of the intersection? So last example. So we're going to utilize the previous theorem in this problem. So this guy says, what is the probability that a positive integer selected at random from the set of positive integers not exceeding 100, and they need to be positive integers not exceeding 100, which means we can include the 100. So S, the sample space, is going to be the positive integers up through 100, and there are 100 positive integers 1 through 100, so the size of the sample space is 100. And it says, let's see, it says, what is the probability that one of these integers in this set is not divisible by 2 or a 5? So I have two events here. I have event 1. I'm going to call it, hey, I'm divisible by 5. And we need to know what the size of that set is. But to get the size of that set, we can just divide 5 into 100, and it's going to go in 20 times. And so the size of E1 is going to be 20. And the reason we can do this division and come up with the answer is this tells us how many integers there are, or if we use them to make multiples of 5, 5 times 1, 5 times 2, ... all the way through 5 times 20, which is going to get us to 100. This is going to generate multiples of 5 that are less than or equal to 100, or between 0 and 100, 100 inclusive. So there's going to be 1, 2, 3, ... There's going to be 20 of them. There's going to be 20 multiples of 5 that don't exceed 100. And we can do the same thing for E2. We can make E2 be the event that I'm divisible by 2. But there's just going to be 2 goes into 150 times. There's going to be 50 numbers divisible by 2 between 1 and 100. So the size of E2 is going to be equal to 50. But if I start adding up probabilities, I'm going to get overlap because some numbers that are divisible by 5 are also divisible by 2 and vice versa. So there's numbers that are divisible by both 5 and 2. So we need to look at the intersection. So E1 intersect E2 means divisible by 5 and 2. And to figure this guy out, to figure out what elements are members of this intersection, we just need to work out the least common multiple of 5 and 2, which is 10. 10 is the first number that both 5 and 2 go into evenly. So how many times does 10 go into 100? It goes in 10 times. There's going to be 10 numbers divisible by both 5 and 2. It's going to be anything divisible by the least common multiple of 5 and 2. So in other words, if we skip count by 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, we get 10 positive integers that are divisible by both 5 and 2. So now we can calculate our probability. The probability that we are divisible by 5 or divisible by 2 is just equal to the sum of the probabilities. So the probability that of E1 plus the probability of E2. And then we have to get rid of the double count. So we have to subtract off the probability of the intersection. So the probability of E1 is going to be how many numbers are divisible by 5? There are 20 of them. Divided by the number of elements in the sample space. There are 100 elements in the sample space. Plus how many numbers are divisible by 2? There are 50 of them. The size of E2 is 50. Divided by the size of the sample space, minus how many elements are in the intersection, divided by the number of elements in the sample space. So we get 20 plus 50 is 70, minus 10 is 60 over 100, or 6/10, or 3/5, or as a decimal, that would just be 0.6 or 60%. So that's the probability of the union of those two events.